All right, so geometric sequences, this would go along with assignment 31 if you're in my class, or in general, how to work with geometric sequences presented as tables, graphs, and word problems. We'll start with a table where you can see we have a counter row on top, 1, 2, 3, 4, and a list of numbers on the bottom which clearly are formed by multiplying over and over by the number 3. The first thing we're going to look at is the explicit formula for a geometric sequence. The formula is given as so. This formula is available on your formula sheet. To fill out this formula, we need a sub 1 and r. A sub 1, remember, is your first term. So your first term on the bottom row of this sequence is going to be 7. R represents your common ratio, which is what you're multiplying by over and over. For this table, it's pretty obvious you're multiplying by 3. But if it's not obvious, you can always divide the second number, 21, divided by the first number, 7, to get the 3. To get the explicit formula, you simply insert the 7 and the 3 into the formula. For the recursive formula, again, you're given that formula. We know it's recursive if you see a sub n minus 1, which always represents the previous term. To fill out the recursive formula, I simply need r, which has already been established to be 3. Notice I filled 3 in for r here, but I also put the footnote that a sub 1 is equal to 7. When you're writing the recursive formula, that footnote is not necessary, but if you're writing the sequence from the recursive formula, it is needed. So I'll go ahead and put the a sub 1 is equal to 7 there, though you would not absolutely have to on your paper. C asks for the domain. I need you to know that domain is all possible x values. If you look at this table, all we have are 4 what we call discrete values. I know nothing before 1 nor beyond 4, nor do I know anything that happens between those numbers. So my domain here is simply the list of x values. Similarly, the range is associated with all possible y's. I know nothing before 7 or beyond 189 or what happens between those y values. So my range here will simply be a list, 7, 21, 63, and 189. Now let's look at the exponential function, which is another name for geometric sequence, with a graph. We're going to ask the same questions, the explicit formula. Again, the formula is given. Here we need to find a sub 1 and r from a graph. A sub 1 is the y value associated with x coordinate 1. So you can see here with the arrows pointing that a sub 1 is equal to 2. Again, it's that y value associated with x coordinate 1. R is what you're multiplying by over and over. And here it's not so obvious. I have a 2 and then somehow I get to a 1. Well, what must I multiply 2 by to get to a 1? Well, to find that out, you would divide the second number 1 divided by the first number 2, which is simply 1/2. You could represent that, if you wanted to, by 0.5. To write the explicit formula, I'm going to put a sub 1 and r into there. So I get a sub n is equal to 2 times 1/2 raised to the n minus 1. Recursive formula, again, I need only r, and I plug that value in. Again, making the footnote that a sub 1 is equal to 2, which is not absolutely necessary, but helpful. The domain and range is distinctly different from a graph than it is from a table. With a graph, I can physically see that not only do I have the 3 points you see, but also everything before the first point, beyond the second point, and in between those points. Since domain is all possible x values, I look at everything on the horizontal axis. So what's to the left of the horizontal axis would be your x-axis here. It goes forever to the left and forever to the right. Okay, it appears that this graph will continue off the page to the left and off the page to the right. For that reason, I say my domain here is all real numbers. Okay, again, a little bit different because you have to think all possible x values, which goes along this horizontal axis, and it does appear to continue forever. Range is a little different. It's all possible y values, and y values are associated with this vertical axis. Well, you are going to go up forever, it appears, but it looks like you're going to stop going down here. As a matter of fact, we call this x-axis an asymptote, a line that a graph approaches more and more closely, but never actually touches. For that reason, we say our range here is y greater than 0. That is, it goes down to 0. It doesn't actually touch 0, but it goes down to it, and then from there it goes up forever. Remember the key here, domain is all possible x's, range is all possible y's. Let's look at a couple. Fuel efficiency of a car decreases by 8%. Brand new, the car gets 32 miles per gallon. Where x is in years, the model showing fuel efficiency is given. You may notice that you start with 32 on year 0, and you're going down by 0.92 each time. So the first question here, what's the common ratio? Well, we know from our positioning from the geometric formula a couple slides ago that the base is in the position of common ratio. So you're going to be multiplying over and over by 0.92. As a matter of fact, that's what an exponent is. It's simply repeated multiplication. So I'm going to multiply over and over by 0.92. First term actually is a little bit tricky here. Depends on if your exponent is x or x minus 1. If you're ever in doubt about what your first term is, simply plug 1 in for x. So here if we do that, the first term is after 1 year, okay, is 29.44. So 1 is associated with 29.44. The 32 actually here would be associated with 0. So it's a little tricky because a lot of times we're thinking, well, 32 is always the first term, but it depends on your exponent if it's x or x.1. So just plug the 1 in if you're not sure. The recursive rule, again, requires r, which has already been established. Okay, now this is a typo here. That should say 29.44, so please make note of that. That should be a 29.44 here, not a 32. Okay, on the next slide, what's the fuel efficiency after 4 years? Okay, well, you just simply plug a 4 into that, and you can see 22.92. All right, so unsurprising that the fuel efficiency continues to decline as the car gets older. It may be time for a tune-up if it's dropped that much. On top of word problem, you may be given a sequence. Again, it's a geometric sequence here. It's not a table or graph. It's just a list, which is the easiest presentation. We're going to ask some questions about this. First, what is a sub 1 and a sub 3? Just some understanding of notation. A sub 1 is the first term, so that would be 3. A sub 3 is the third term. Okay, so what's your third term? 1, 2, 3 is 48. What's a reasonable domain here? Now, this is a little tricky because you're not given the table, but for a sequence in general, the domain is just a list of counters, a list of counting numbers. 1, 2, 3, 4. And notice the dot, dot, dot. It does continue because the sequence continues. So envision this being in table format. You'd have 1, 2, 3, 4 above that. Range, of course, would be just the numbers in your sequence. So you just have to think of it as a table to answer that question. Finally, what's the common ratio? Again, we've already established that. The common ratio here would be pretty clearly 4 here. If you're not sure, it's the second number divided by the first number. So it would be 4 in this example.